Okay, let's continue with Unit 2, soil-plant relationships, and let's tackle objectives 3, 4, and 5. And these objectives are that you should be able to list the functions of roots and describe where they take place within a root system. You should be able to describe, this is objective 4, describe the mechanisms of root interception, mass flow, and diffusion, and how these three supply nutrients to plant roots. And then tied directly with objective number 4 is objective number 5, to be able to list the primary mechanism responsible for nutrient transport of nitrogen, phosphorus, potassium, calcium, and magnesium with respect to root interception, mass flow, or diffusion. So let's talk about first the functions of roots. And some of these, I hope, are new to you and some of them are not. So one of the main functions, in fact, the main function of roots is to anchor the plant in the ground. The entire root system does this. But with respect to corn, adventitious roots do this very well. And so what you see with corn, and maybe you've seen this, and if you haven't, sometimes stop by a cornfield here in the Midwest and just walk out to the very first row of corn, and you should see these claw-like adventitious roots digging into the soil. And these are really used for anchorage. In fact, some of these adventitious roots in corn attract microorganisms, in some corn, attract microorganisms that can capture nitrogen from the atmosphere, which is really, really interesting. And scientists are actually looking at means by which we can code other corn varieties with that particular aspect to capture more nitrogen from the atmosphere or capture nitrogen from the atmosphere instead of applying inorganic nitrogen fertilizers. So if you're really interested in something like that, it's a great avenue to pursue in terms of a career. So the first function of roots is anchorage, anchoring the plant in the ground. The second function, we talked about this with respect to the first two objectives, absorption, right? So absorption of water, absorption of nutrients, and this occurs in the epidermis and specifically the root hairs. The third function of roots is storage. This is storage of carbohydrates, and this occurs in the cortex, but in order to pump carbohydrates down into the root system, you need the vascular tissues or the vascular bundle. You need the xylem and the phloem. It's the only way to do this. So those two go hand in hand. The cortex and the vascular tissue are used for storage. And the fourth means by which roots function are for conduction. And this is the conduction of carbohydrates down and nutrients and water up, and that occurs through the vascular tissue. So there are the four functions of roots. Now, let's tackle objective number 4. There are three mechanisms for nutrient transport to the roots, and these mechanisms are considered passive transport mechanisms. And what do I mean by that? What do I mean by that is that these three mechanisms are used by the plant to capture nutrients, but the plant doesn't have to expend a lot of energy. And so we consider these passive. And these three mechanisms are root interception, mass flow, and diffusion. And those are illustrated in this diagram on the bottom right-hand corner of this slide. So root interception is very simple. The root's going to grow no matter what. Well, almost no matter what. And if it's normal, under normal conditions, the root's going to grow and a root hair is going to emerge. And if a root hair just so happens to touch a nutrient in the soil solution, like this red dot here, whatever that is, I'm assuming that's calcium, it can automatically absorb it because it intercepts it directly. Mass flow is simply the movement of soluble ions towards the root in the soil solution. And this is driven by transpiration. So the root is taking up water and it creates a gradient by which water flows towards the root itself. And when the soil solution or water in the soil moves towards the roots, it carries soluble ions to the root that can be absorbed. The third means is diffusion. And diffusion occurs on a really small scale. We're talking 1 to 2 centimeters per season, per growing season. And, uh, and you're going to learn about this in a little bit more detail here in a few minutes. But for example, phosphorus diffuses only 1 to 2 centimeters per year. It's not carried very well through the soil solution. And in fact, it loves to be loved, and it does not love to be by itself in the soil solution. So these ions diffuse 1 to 2 centimeters per year, and then they reprecipitate, and then they dissolve, and they reprecipitate, and it's lucky that the root can actually see it itself. And so we're going to talk about how this works in soils with the next several slides. So root interception, what is it? It's simply nutrient uptake that occurs when there's direct contact by the root for the nutrient, right? So the root is reaching out as it's moving through the profile. Actually, it's the root hair. And if it touches, for example, in this case, it touches potassium, it can take it up. The quantity of ions intercepted via root interception depends on the concentration in the soil solution. Is it high or low? And it's dependent on the percent of the soil that's explored by the roots. And this is a real bummer for plants. Now, plants grow and they thrive. We all know this. They thrive well, but the roots usually only see 1 to 3% of the total soil volume, and they maybe contact a maximum of 3% of the soil nutrients. So they're not really seeing that much. So it's amazing that plants can actually not show you a deficiency symptom. And they don't show you a deficiency symptom because there are other mechanisms by which plants see nutrients besides root interception. If a plant had to solely rely on root interception, it would die, all right, because it doesn't see enough of the soil. So let me share with you a table. Here are the 5 nutrients that I want you to focus on for this unit: nitrogen, phosphorus, potassium, calcium, and magnesium. This is roughly the amount of available pounds per acre in a soil. If the root, and we'll pick a middle number in this range, let's say the root contact is only 2%. So 2% of the amount available is what the root sees via root interception, which are these values here. And if we're growing corn, which is the king of nutrients by far out of almost every single plant that's grown, the amount required to grow a relatively, quote, normal amount of corn in bushels per acre, 240 bushels per acre, is this much here. All right. So this is what's required to raise 240 bushels per acre corn. And this is what the plant sees in terms of root interception. And if you do the math, the percentages tell you that the amount of, for example, nitrogen obtained by root interception by corn is only 1.7%, 4.7 for phosphorus, 10% for potassium. And now we're really starting to talk here. For calcium, it's 145%. And for magnesium, it's relatively high, about 60%. So in terms of root interception, I would say that calcium and to some extent magnesium are driving factors for root interception and uptake by plants. The other 3 macro elements, there's no way a plant would survive via root interception alone. So how do plants overcome this? Well, plants are not stupid. They're very smart, and they've modified themselves over time to find and seek out nutrients by other means. One of the other means is mass flow. And what is this? Mass flow is simply the process of dissolved nutrients that are transported to the root surface by water movement. And this is driven by transpiration. So this is driven by a water gradient from the soil solution out here via water uptake by the root, which transports water up through the plant, through the vascular tissue, through the xylem, and out of the leaves through the stomates. And there's a gradient, and that gradient creates a gradient in the soil for mass flow. So it creates a gradient for water, but it also carries nutrients to the plant root itself, driven by transpiration. And so here's a table. You just saw a table similar to this for root interception. This is for mass flow. The same nutrients, the amount that's typically found in the soil solution, the amount that's required by corn, and then the amount that's delivered by mass flow. And if you do the math for these two columns, you'll see that nitrogen, the amount of nitrogen obtained by mass flow is 120%. Not much for phosphorus, not much for potassium, and certainly a great amount for calcium and magnesium. And so mass flow drives nitrogen, calcium, and magnesium to roots, by and large, okay? And we're going to talk about these individually when we get to those units. So diffusion. Diffusion, what is it? Diffusion is simply ion movement resulting from a concentration gradient. So movement resulting from a concentration gradient. Ions move from a high concentration area in the soil to a low concentration area in the soil. And if this first graph on the top right makes sense to you, that's great. All right, so here's concentration. And this curve here, curve A, is the curve of concentrations in from the soil, from a soil particle into the soil solution. And the curve for B is the concentration right near the root out to the soil solution. Right? Another way of describing this is in this picture from A to B. And maybe you did something like this when you were in elementary school, where somebody put in a membrane that you had a greater concentration on one side of the membrane, you put a dye in it, and then the dye migrated to the other side of the membrane. The same concept holds true here. Concentration of some ion is very high. This is oftentimes right next to a soil particle or a fertilizer particle, and the concentration near the root is low. And that gradient drives ions from a high concentration to a low concentration. So let's talk about this specifically. So this is what happens. Nutrient uptake by the root decreases the concentration in the soil solution near the root, and it creates the gradient, right? So there's some factors that affect this. And one factor is the concentration gradient itself. It increases with decreasing nutrient concentration next to the root. That should make sense because the root is absorbing the nutrients. There's less in the soil solution right next to the root, and then there's a concentration gradient that's created. Soil moisture is key for this process, much like mass flow, right? Soil moisture. You need to have soil moisture for diffusion to occur. So increasing soil moisture decreases water tortuosity in soil, and this increases the diffusion rate. What do I mean by tortuosity? If the soil is relatively saturated, the path between point A and point B is relatively direct. But if as the soil dries down and pores are filled with air and not water, now the water has, or the ions that are diffusing have to follow a path through the soil, through the pores that are filled with water to the root, making it more difficult for diffusion to occur and the plant to see the nutrient. This is driven by soil texture. Coarse textured soils have lower tortuosity, higher diffusion rates, and finer textured soils have more tortuosity and lower diffusion rates. The kicker is, and you probably remember this, is that coarse textured soils hold less water than finer textured soils. So there's a trade-off here. A fourth factor that affects diffusion is temperature. The greater the temperature, the greater the diffusion rate. And then finally, distance. Diffusion is really slow, and it occurs only over 1 to 2 centimeters within the soil. yet it still has a major impact on nutrients like phosphorus and potassium. Okay, so let me share with you this summary slide. This is a summary of macronutrients supplied by roots or supplied to roots by interception, mass flow, and diffusion. And we talked about nitrogen. And so here's nitrogen, this first row. Root interception is very low. Mass flow is incredible. And this is because of the form of nitrogen that's transported in water, which is often nitrate, which is negatively charged, and it's water soluble. And there's no diffusion. There's simply no diffusion of nitrogen in soils. Let's talk about calcium and magnesium. Calcium and magnesium, the amount that's supplied by root interception is relatively great, but mass flow dominates. And diffusion is zero. Really, calcium and magnesium ions or minerals dissolve either relatively easy or not relatively easy in water. And when they dissolve in water, regardless, they're transported by the root via mass flow. Phosphorus and potassium are different. And phosphorus, as you're going to learn in the phosphorus unit, unit 6, loves to be loved. It loves to be bound to soil mineral phases. It loves to be bound as precipitated minerals themselves. And it does not like being in the soil solution. So it will dissolve and it'll diffuse 1 to 2 centimeters in a growing season, and then it'll be gobbled back up by either a by a mineral phase, or if the plant's lucky enough to see it, a plant, or a microorganism. The same basically holds true for potassium. The potassium minerals dissolve, potassium gets caught within interlayers of clays, they get stuck on the outside of clays, and eventually this process goes back and forth, and it basically ends up relating potassium to diffusion over 1 to 2 centimeters throughout a growing season. And we're going to talk more about potassium in Unit 7. So, which nutrient uptake mechanism is most important for each of the above nutrients? We just outlined that. And then I added, what about AM fungi, arbuscular mycorrhizal fungi? These are fungal mats that are symbiotic associations with plants. About 80% of plants on the face of the earth have this association. The fungi look like root or roots, and in fact, they're an extension of roots, whereby these fungi explore soils for nutrients such as phosphorus, potassium, maybe nitrogen, and water, and supply those nutrients to a plant, and the plant supplies energy in the form of carbohydrates to the arbuscular mycorrhizal fungi. And this arbuscular mycorrhizal fungi association helps the plant explore or see more of the soil, thus seeing more phosphorus and potassium than the plant otherwise would. So plants are not stupid. They're very smart, and they've formed associations with microorganisms to explore more soil.